So again, welcome. And then we're mainly an on-site course, so a few housekeeping rules, but the important thing would be if you have any questions, you can raise your hands, and we have our experts here, and Marion and I are also around to help you whenever you have questions during the sessions. And feel free to ask questions. And like in the previous parts, also we always want to have a welcome from the European Union ambassador to the Philippines. So we'll just start with this video.
State where, as the European Union ambassador to the Philippines, I am very honored to represent a European Union made of 27 European countries with a shared commitment to peace, prosperity, sustainability, and democracy. The European Union is not just a political and economic union. It is much more. It is a global partner with values cooperation, inclusivity, human rights. Here in the Philippines, the European Union has been a reliable and consistent partner for over 60 decades, who support a very wide range of initiatives, from promoting peace, good governance, human rights, to enhancing common security in a complex geopolitical context, advancing digital innovation, trade, disaster risk reduction, green economy, and much more. This long-standing partnership reflects our deep commitment to working hand in hand with the Philippines in building a more sustainable, resilient, and inclusive future where no one is left behind. In the Philippines, a country especially prone to hazards and the consequences of climate change, this means supporting initiatives which create real opportunities for communities, foster innovation, build resilience in face of these global challenges. And in this context, the Philippines stands to benefit immensely from the integration of Earth observation technologies. This will strengthen the country's capacity to address climate and hazard-related vulnerabilities and will support biodiversity conservation. I am very proud, therefore, to introduce CopPhil. CopPhil is a unique flagship initiative of the European Union Global Gateway Strategy. It is managed by our team here at the European Union delegation, and it is implemented by the European Space Agency in partnership with the Philippine Space Agency and the Philippine Department of Science and Technology. CopPhil promotes the use of free and open satellite data from Copernicus, the EU space program's Earth observation component, through activities including the establishment of an IT infrastructure and Copernicus mirror site for accessing and processing Copernicus satellite data on biodiversity, on forest management, on agriculture, for example. This transfer of data is reinforced by the CopPhil training program, in which we are very excited to co-create with institutions across the Philippines. These courses build a shared understanding of value and the practical applications of Copernicus satellite data. Together, through CopPhil, we are advancing a partnership to empower the Philippines to become a central hub for Earth conservation in Southeast Asia and supporting its path towards a more sustainable and resilient future. I would like to sincerely thank all of you, participants, as well as our partners and stakeholders who have made this training possible. Your dedication, your enthusiasm are the foundation of the CopPhil success, which is a very important joint initiative together with our Philippines counterparts. Let's remember that our progress relies on ongoing cooperation, shared learning, mutual support. The challenges in front of us are complex, this we are very aware, but it is united in purpose that we can build lasting solutions. Thank you very much.
So again, good afternoon, and that's a few words from the European Union ambassador and introducing us the CopPhil project, and also welcome to our more participants. So welcome, and just for you, we have here the credentials for the Wi-Fi. Also, we have sent a link for to download the materials for today. So maybe just a few moments you can also connect and try to start downloading them. But I'll continue with the rest of the presentation. So here we have the whole CopPhil Earth Observation Pilot Services training, and we started with an introduction to CopPhil, and then we had part one theoretical courses, part two more on the fundamentals for the EO services, and then we're now here with the application courses. So the part three courses we're in, we'll try to use what we've learned from the theoretical courses and the fundamental practical courses to really apply what we've learned from before. And we've launched series of training sessions already from last year and in different EO services. So we have three main CopPhil services. So the ground motion, and then the second one is the land cover, forest and crop, and the third is benthic habitat. And right now we're doing the application course for the ground motion. And then short highlight that everything we will wrap up this week. We will have a final event. So from your invitations, you've already also read that we'll be having the first contact event on August 8th. So feel free to check out the further details that we've sent you, and you're all invited to attend this session. So again, so after having all these trainings, you can access all the materials in our digital campus. So this is our training platform. And then it's also here wherein you need to create your account. We're already at part three. You have all the courses in there, all the course details. And then it's from here that we just have short assessments, so just a few quizzes and also a feedback form. After doing those things, you can earn your certificates, and then we're good to go. So again, for this training program, we have our experts from University of Twente, ITC from the Netherlands, and also experts from GMB Romania. So our experts are here today to talk about what they've been doing in developing the ground motion service. And we're happy to have them here, and I think we've all seen each other online, and now they're here. So everyone is excited to have you all here also. So we have Dr. Ling Chang, Dr. Pingshan Lee from ITC, and then Mihaela and George from GMP. So also thank you for your time, and then I will transfer over to you, Prof. Ling. So um, welcome, and then I think we can start the session right now. Yes. Yes. Oops. Oh, it's fine. Okay. We can exchange. Yeah. We can exchange. Okay.
Good afternoon, everyone. My name is Binchuan Li. In this part, I will introduce you how to use the GOV platform to process the how to use the GOV platform to process the Sentinel-1 data we are interested in. Please visit the URL regarding the URL and username or password. I think GOV will distribute it to you. In short, on the when we open the URL on the top right of the page, we can find the authorize button. Click on it. We can see the authorizations dialog. Here we should input your username, password. For this kind of credentials location, we should select request body, then click authorize button. Click, scroll down the page. We can find the ground motion service here called inside ITC. Then we click try it out button. Here we can find the input interface of parameters we need to fill in. For CopPhil, here we can upload JSON file or CopPhil file. Here we upload the CopPhil. For the ST represents start date for processing. Here we put 22 January 1st. So ED represents the end date for processing. Here we input 2024 December 31st. Method we in the platform we have two methods here. We select sparse method. Orbit we have this platform has descending and ascending direction. Here we select direction. Temporal baseline we select 24 or 20 in 12, 24 or 36. Here we input 36. Mountain looking, here we can input 20 and 4. When we finish the parameters, then we should execute the button to save time. I have click execution button in order to monitor the task. We should visit the URL. When we open the URL, we can see the running job. We can click it, then click this one. We can the metadata. Metadata is displayed. I think it is for us, it is important parameter is user ID or order ID or user ID. According to the user ID and order ID, we can download the results. When the task is placed, we can download the results. In this terminal, we can download the results. Sorry. This is your user ID. This is user ID. This is order ID. This is path represents the output folder. To save time, I have downloaded the results in advance. This is the results can include JPEG and the XML. We can open it with QGIS and or ArcGIS. We can use the INSA Explorer to visualize it. Here we can set the value 100 and 100 and then applied it. This is the result. This is the velocity rate map. Then we can choose the point to check its deformation time series. This is the deformation time series. I think it is okay for me. That's all. Addition, we have finished the sparse results for Manila. GOV is performing for visualization. I think we can look for the results in GOV platform. Thank you. That's all.
Yeah, to complement. So let's see. So there are another link called link 2, I guess. So actually you can download this geo package format like Yichuan showed. So if you're interested, like I mentioned, you can download the smallest one and then simply visualize it from ArcGIS or QGIS. And to visualize it for your information, actually, if you don't really have this INSA Explorer installed, you can always go to this manage and install plugin and try to find this INSA Explorer. And then you can easily visualize the results that Binchan just showed you. So this is small things I would like to share, and let me continue. After that, we can have a short break. I think I'm sharing. For the moment, actually, we managed to generate the 9 things for the last 3 years. And here you can see that we list, let's say, the path and the frame number for these 9 things. And I'd just like to directly show you the results. You can see how this, let's say, Spark product was generated. So this is, let's say, the result mainly covers most of the area of the noodle. And you can see that from this graph, we still show the deformation velocity map on the boogers. You can see the color dot represent the deformation velocity range. And still, this blue dot showing that that region around the same. So for the geo package, actually, it includes the same information. So if you'd like to test it, you can simply check our sample data. And then I also like to, let's say, showcase the 1.3 product, which indicates the horizontal and vertical deformation components derived from ascending and descending data. So for that case, actually, we use the data set which are far a bit early, between 2019 and 2020. So this is the happening date here. And we use the Sentinel-1B data set with 16 one images in total. And in the end, you see that we generate more than 300,000 sparse point images. Let's see. So we also share this Python script called Python 3D tensors type. Actually, it can do this line of sight decomposition directly if you define the ascending output information output and the descending information output. Here, I just give you the 2 different names. And then this map indicates the vertical deformation component over the overlapped areas for the Sentinel-1A and Sentinel-1B. And you can see that, let's say, which area moves much faster in vertical direction. And of course, we can also generate the horizontal deformation in the east-west direction. And then you can see that, in principle, how much this area moves horizontally. I also like to draw your attention. So actually, for this kind of result, you still need to interpret it carefully, because for the moment, we just based on the, say, the geometric matching. So we just identify the ascending and descending data sets, which have the closest distance in space. But we didn't really consider the physical character matching. So suppose there are 2 sparse point, one collected from the Sentinel-1A descending, and another one collected from the Sentinel-1B ascending. Even they are close by, but they represent a different ground feature. And when we do this kind of decomposition, we didn't really, let's say, identify the physical difference. So it means that when we do this kind of decomposition, it may still include the error. Now I would like to move to the Jupyter notebook. I wish that you already download dataset, and now we can, let's say, have a quick try. So I think for your information, I think you may not need the, let's say, the account for the map box. You can directly use the one that I already put on the Jupyter notebook. Then I think all the, let's say, lecture material, I think you already downloaded, shared by Carla. And for the, let's say, the Jupyter notebook that you can actually use Anaconda, for instance, but you can also use Colab. So if you have the Google account, you can also use the Colab to, let's say, open our Jupyter notebook. I don't really know why it's flashing. But I can hold it here. Let's see. And some of you already opened the Jupyter notebook. If not, you can always approach Binchen, so he can help you. Yeah, so he's there to help you individually. Yeah, I think after my short introduction related to this Jupyter notebook, I propose that we have maybe 10 or 15 minutes break, and then we move to the mining application part. Yeah. So here you see that for this one, it's rather basic. We just like to show you that if you download the CSV format data output, how you can read it, how you can interpret it. And in this case that, for instance, you need to, let's say, activate this third-party package, for instance, pandas and also the plot LOL, because we want to visualize our results interactively. So I just click this button. I think it should be very fast. So here you see that I would like to visualize all the output for these 9 frames. And then I just simply run it. I think it won't take too long, so that's why I just directly run it. And for your case, actually, you can also try. If you already place all this file on the same folder that we share on the subdrive link. Yeah, another thing I would like to mention. So here, actually, you see that for the file, geo package have a different naming. Yeah, so I have to say that in the end, actually, we will stick to this type of naming for the final output with, let's say, the CAPH, CopPhil project abbreviation at the beginning, and the ground motion service with the P1.1 product and the path and the frame number, and then the orbit direction, which descending, and then acquisition time. So you see that in the end, you already extract some basic information from the name of the final output. And also it's nice that you can also visualize the XML file if you like. I think I can also have some example. One moment. Meanwhile, I also open this one. I just like to show you what kind of basic information we include there. In the meantime, I can also initiate this part. So you can see, so for our case, actually, we also use this Luzon Island group shapefile to help us to only include the results covering the Luzon region. And actually, this is an optional step. If you like to visualize all the results for this 9 frame, you don't really need to do that, because we only do this kind of, let's say, filtering for the acquisition for this one with the pass 36 and the frame number is 551. And just because for our output is let's say saved in the WGS 18.4, so that's why we stick to this EPSG with 4,326. It's a bit slow to open that one, so I just continue. Just because I already, let's say, share this output in our self-drive link, actually you don't really need to run this step. You can directly skip this step and then go to this one, because the idea just like to see that whether we keep the same content after the filtering. For instance, we keep, let's say, all this kind of attribute, including code. I mean, the sparse point ID, latitude, longitude, height, velocity, all this kind of information in this filtered CSV file. And in total, we have this amount of points remained. And then we do the visualization. So just because for the sparse results is still quite a big data set, that's why we do the kind of sampling with a step of 100. So if you also initiate this part, you will see that yeah, it will visualize the result in this map. Let's wait a while. Yeah, so you will see actually the same results that I just show you on our points. But for that case, I use Google Earth. This one we use the interactive map on the Jupyter Notebook. And then I think you can also hover around your mouse to see the location and also the velocity. And then for this, the next step, actually, I also like to, let's say, include the outline of the Luzon region. So that's why here, if I run this step, to take a bit of time. Yeah, I think meanwhile I also open this XML file just to show you what kind of information we have here. So actually this is similar like the metadata from the Sentinel-1 dataset, for instance. It shows the product level that I would just mention. It's in long side direction, so that's why it's P1.1. And also included, let's say, the coordinate reference, which is WGS 18.4, and which DM we use, and also indicate I think the mean incidence angle, and also the, let's say, the orbit angle, because this is a descending data set, that's why it's negative, for instance. Otherwise, it will be 300 plus something. No, it will be 119 something. And then it's include all the raw data set information with this name written here. So if you open this XML file, you will know that how many sign images are processed and what's the, let's say, the starting and end acquisition date, please. Yeah. So in total is 18.8 for the 3 years. Yeah, and then let me see whether I finished or not. So I finished this part. You see that this purple color just outlines the Luzon region. And apparently you can see, for instance, for this kind of island located to the south, actually we didn't really include for the processing. If you're interested, actually you can, yeah, finish this part. And then let's see. Yeah, now I also like to showcase the P1.3 product. Here I use acquisition acquired between 2019 and 2020 for 2 years. both ascending and descending data set. So if you click, I hope it will be fast. Maybe I don't really need to run here one by one. Let me see. Maybe I can directly explain, because I think those are some, let's say, the information I already introduced for the last training course. Actually, you can always go back to that one. This goes fast. Yeah. So this one we don't need it. And for the sample data, also finished. So it will be very fast. So actually, for this case, you can also easily visualize the sparse result for the descending data acquired by channel 1A. The things I would like to draw your attention is that when you visualize the velocity, for instance, for the sparse result, you see that for the expectation, here the mean value actually not 0. But the last time when we showed the sparse result, we showed that actually for that case is 0. It's the main reason is because for the sparse, actually it's do the averaging in space for all the acquisitions. So that's why they, let's say, internally make sure the expectation or mean velocity always go to 0. But for the GMT side, it's another case. So they didn't really select any reference. And here you can see apparently the mean value is not 0. So when you do this kind of interpretation, you always need to know this kind of basic information from different software. And I do the same trick to read the channel 1B. It's running. Yeah, I think you can try it after the coffee break. And I just like to, let's say, check in. See. Yeah, here's very interesting. I would like to see whether I can, you know. So you see that, see. So we have this kind of intermediate output to show the interferogram information. And in principle, we can also visualize them here. Let me just to make this a little bigger. So I just visualize that inside tab file, you can see it's indicated the, let's say, the directory, and also indicate the acquisition date between two acquisitions to form the interferogram. Based on this information, we can generate this spatial and temporal graph this way. So actually, you can also play with it and to understand how it's generated interferogram based on to SLC dataset. So this is for the channel 1B. Let me just yeah, here I also show you how you can visualize a deformation time series for a selected point. So later, actually, Georgia and Mihaela will give you more examples. So I don't really explain more here. Here I still draw your attention. So how you can estimate the velocity afterwards, considering the intercept in the y-axis, because for this deformation time series, it's not necessary have the 0 intercept. So this one actually is similar like what we presented last time, so I just skip. But for your case, actually, you can also simply click and check the result. Here you see that I command this part to do the line side decomposition. If you like to initiate this part, you can simply remove this hashtag and then run it. Then here I just show you this result after the line side decomposition. Okay, it's finished. And then see. Yeah, for this part, let's see. it moves too fast. So for the vertical time series means that we generate the vertical deformation component in vertical from the long side displacement, and the horizontal represent the movement in the horizontal. Let's see. So this is the map that I just show you on the slide. Represent the vertical deformation component. The area actually the overlap region between ascending and descending data. Then we can also visualize the horizontal deformation. So for this one, I think I can it's loading a bit. Yeah. So if you just move around your mouse, you can always let's say see how about the location and also the values that just estimated. And if you like to, for instance, just to pick up some points, I just skip this one, just to like to see some, this part, maybe we can directly see it. Yeah, so for this command, you can see that I just like to visualize the point with the index with this number, 91107, and then I identify its latitude, longitude, even the velocity in vertical and horizontal direction. I want to see these two components for this selected point. And it's visualized on this map. You can see for the red dot indicated the horizontal movement, and for the vertical, it represents, the vertical deformation time series shown by this blue dot. And you can see for the horizontal, it seems to move smoothly upward, and for the vertical, it's moving downward, quite, let's say, considerably. And here, yeah, so this is a bit small, but still, I hope we can see for this map, just indicate the location on the map. So it can give you a bit of feeling if you select the point, where it's located. And this can also help you to have a better interpretation, whether this deformation time series or vertical and deformation component estimation making sense or not. I think that's all for the first part. So let's have 10 minutes break. And yeah, actually, George and Mihaela bring some nice biscuit from Romania, and we also buy some cookies. So we hope you can, let's say, yeah, enjoy. Yeah, we 10 minutes. Yeah, we start at 5:03.
Yes.
Yeah. Thank you. I think I can ask Rob a question. If
Okay.
no, I think I move the hand to George.
Yeah.
I can still.
Yes. Yeah.
You need to shoot 2 seconds. I think tomorrow.
Hi, so break time 10 minutes, but we also have some snacks for you guys. So yeah, please feel free to take some.
I'm working for the CopPhil project. I want to know why you did so further. You started, I think, 2019. why did you go to?
I think for the this is coming from you. This one? Oh, no, I think from George.
From Romania.
I'm not sure. So the coming from Europe, they've been covered by China. So it's from Romania and Lebanon. No, sorry. We only have the local. Yeah, actually we can. But I think for the translation, actually, just to take the shorter period of
Marine, where's the rest?
Okay,
Okay, I will just.
yeah, we mentioned that we just focus on the affirmation for the last 3 years. Yeah, definitely we can read up to 14 to 115.
I was involved in the Copernicus activation that was done here. So, and we went in 2000, when it started, 2014. So, but it was in 2021, I think. So it was the data was.
Everyone, what you're hoping your stats flow would be passing around and then. And then after the
The Resilience Institute or the activation?
No, it's SPISA. We use SPISA to have the result, also validate the result. And also, we use a common software, it's commercial software to validate the results. And actually, for this software, actually, we also do some simple tests in the Netherlands. So we sure it works. And also parameter, we also adjust the baselines on the say test.
I now get the data reproduced in with the data from the European Resilience Institute here. There's about 10% difference, which is not bad. One other question is some
Seal damage. Seal damage.
temporal.
Yeah, seal damage.
Yeah.
Yeah, it's related to the future.
Because we didn't have that. That was the activation in 2021. It was more consistent, not completely. I mean, we did also with the dynamic analysis. So whether it's increasing in speed or it's decreasing in speed. We found quite a number of points, but it was not very consistent. So say in a certain area, we found points which are increasing and also points which are decreasing.
Okay.
So, which of course in the end isn't it?
Yeah, because so far actually we do this kind of spatial temporal filtering to remove atmosphere. But I think if the parameter is not set properly, you will see this kind of pattern.
I mean, it's good. I don't know, but I mean, some of this ground motion is also depending on seasons.
Yeah,
So in the rainy season,
you usually have.
yeah.
Yeah.
So, but we didn't see that. I mean, we did 6 years or so. We didn't see seasonal patterns actually.
Do you think it's related to the filtering?
I don't know. I mean, it depends really on. Actually, I think in the Philippines, unless it's a very dry season, it's always wet.
Mm-hmm.
So it's in other parts of the world, I think the soil moisture is fluctuating more than here.
Yeah, that's true.
I mean, people say we have 2 seasons, wet season and very wet season. So
Okay. Yeah.
and so what? I guess that actually not so much. I have seen from Greece or so, we could very beautifully see this the seasonal variations. But I don't think it's not here.
Yeah, but at the moment, actually, we're also using the geohazard method to variation. Because we still need to validate our results. So far, we know that the estimation are relative. So we still need to make sure.
We have used points from Nigeria, geodetic points from Nigeria, from the mapping agency. So if they have, I mean, we did Manila and we had up to San Fernando also. We had, I think, 5 or 6 geodetic points with the data from Nigeria.
I think we also have. I think so. I don't remember.
Yeah, something like that. What's about the Malaysia points?
I think so. Maybe from the 3 days. I need to double check. Yeah.
Okay, no, but people just not. Maybe they have them, but then they have them probably from Malaysia. So, because the ones measuring this, I mean, the Malaysia has this really very, say, accurately measured geodetic point. But I think Philo has some GPS all over the country.
Yeah.
But I think that's a different system. But I don't know. I didn't use the GPS points, but I think they have their own network of GPS.
That's usually with the balance. And she helps us to, let's say, connect to the state of instance.
Yeah. You also put data line of sight to vertical.
Yes, so this is the results actually in the vertical direction. This is one selected point roughly located let's see, roughly located here, for instance. And this is the result that we generate for this point.
That's vertical, so it's not
Yeah.
line of sight anymore.
No. But yeah, still for many areas we see the horizontal movement quite a lot. So
Horizon?
Yeah. yeah, it's a bit strange. So that's why I think there could be.
Actually, what we had, I mean, we also did verticals, not much.
Yeah, I think
So,
in essence, I think.
I mean, actually, the geology, at least here in the Manila area, says that there is a strike slip in north-south direction. So you couldn't see much. I mean,
No.
much in the east-west.
Okay.
So there is a fault line through Manila actually, but it's a strike slip north-south. Doesn't help much. To east-west.
Yeah, so that's why.
So we don't expect much at least.
Oh, yeah, I think we also think that there should be not much movement in the direction. So that's why I guess it's mainly because the, let's say, the spatial resolution that we define, which is really close. And for the pair point we select for ascending, descending, maybe they represent different targets. So for instance, one from ascending for the ground, another one which is close by for the building. So that's why our estimation is still quite biased. But this is the thing that we are investigating. For our case, we just want to make sure the software is ready, and yeah, all the people can use it. Yeah.
Yeah, that is still something where I'm also going to.
Yeah.
No, I mean, the idea was to have in the end something like the European one motion service, and that will not happen, I think. Yeah, I like
Extension or there will be one that
I mean, there are two things. One is in general, there is not much of an open data policy here. So if you have data, and the other is that it's simply quite a bit of work, and to do that for the whole country on a routine basis.
Yeah.
So what I think is more likely that it will be on request. So if you want to have data, you can write to filter. You have to go with other reasons. You have to sign a memorandum of understanding. This is when you want to have data from other offices here. So I don't know, that might be that it's working like that, but maybe I'm wrong. It would be nicer, of course, if it's like the European Ground Motion Service, that you can simply access it and download what you want. So, but that is, we are not very close to that. I can check.
Yeah, please, yeah.
By the way, do you know Norman Kerler?
No one can.
No, he's a ITC professor, I think.
What was the name? Norman.
Norman Kerler.
Norman Clark.
Norman.
Yeah, for the UAV.
Hmm?
For the UAV.
I don't know what he is doing right now.
For the UAV. Nature Hazard.
I don't know what he's doing right now.
Oh.
I actually invited him here to the Philippines to do lectures, but that was more than 10 years ago.
He's another department.
Yeah,
Yeah.
I think the last time I heard from him, he was doing with high resolution optical data, also pattern recognition, object recognition.
Also including
Yeah, I guess. I mean, that was already some years back, and I was not very big then. So, but today, I guess, yeah.
No, he made a book on nature habits.
Mm.
UAV and also other.
That is why I'm a specialist for disasters, and so that is the connection here.
There are already work here.
In the Philippines, 30 years. Yeah. But with disasters also on this board since 2007, I think. Yeah, but it's still also a long time ago.
Oh my gosh.
Yeah. But I'm not only working, I've also worked in Vietnam and Bangladesh and other countries as well. But I'm based here. And I'm now based here in Filter, together with Mario and Nina. So I'm not going into the calculations, but I'm interested in the results. So how you do that and so on, but not that I'm doing.
Because we're also willing to connect with feedback. And also, yeah, if you have some prompts to validate, you will be ready to work.
I mean, when we look at this, I have these geodetic points from Maria. Yeah, if it's from 2.7, it might be different. I don't know.
So to move to the next part, I just wonder whether you have any questions related to the first part for this introduction. For instance, related to this kind of product we just introduced, or you have any errors, problems when you run the Jupyter notebook. Yeah. Maybe we can move to the next part. Yeah. And if you still have questions, just keep it, and then we can try to. Oh, you have, please.
Yeah, on the Dutch, there already filtered that those are for event points on.
Yeah, exactly. So actually, for the sparse points, they are all coherent, but only temporarily. So this is slightly different from PS. PS are the points constantly coherent over time, but for the sparse, it's just a temporary coherent. So they are both coherent, but just in time they're different. Yes, please.
The temporary.
Yeah. So you see that when we define this processing, probably just to show like this one. Yeah, if you see this line, actually we define the temporal maximum. So we, for instance, only select interferograms. So this is 36 days difference. And regarding the temporal coherence, in SPART actually slightly different because you consider both spatial and temporal coherence in one go. And that's why I can show it to you. Yeah, this one. Yeah, here you see that we have this unwrap, let's say, coherent setup, which is 0.05. Here actually consider both spatial and temporal coherence. So in essence, different from the spatial coherence that you calculate, because for many cases they are normalized ranging between 0 and 1. And it means that when this coherence approach 1, it means good coherence for spatial coherence. But this one also consider the temporal coherence, and that's why you see it's quite small. Yeah. By default, we define this value, but actually we also release this argument. You can also increase this number if you are really satisfied with the coherence over your study area. So you can also increase to, for instance, 0.1. Yeah. Okay. So now we move to the second part. We had a more introduction about mining. I just you also use this.
No, I have. I don't.
This one.
I can use both.
Oh, okay. So
Yeah. So.
I can just put this.
So hello everyone. Our colleagues already introduced us. I'm Mihaela from GMV Romania. I'm here together with my colleagues George. We are both working in the remote sensing and geospatial analytics division in GMV. And for today, we prepared a mining application using the SPAS approach. Some of you that might have joined the second training might know these slides already, if you still remember them. But last time we didn't have enough time to go also with a more in-depth presentation of the mining application. And now we considered that we should also present to you an application here in Philippines using the SPAS approach that was, since the second training, chosen as the definitive method that is going to be implemented on the geohazard platform, and is already actually started being implemented there. So just a recap, for us it's interesting to divide the types of mines in open pit mines and underground mines, because we are interested in the associated structural failures that we can meet in these different situations. So in the case of open pit mines, we have large scale surface mining where minerals are extracted from open pit mines because they are found closer to the surface of the earth. In this slide, I added some examples. The Bingham Canyon mine, which is one of the largest mines in the world, and is found in the US. And the Tampakan Copper Gold project, which is found here in the South Mindanao. And for underground mines, we have mining operations that are going for extractive operations for resources that are found at deeper levels. And usually these are happening through underground galleries, tunnels that tend to fail. So we have open pit mines, we have underground mines, and the type of structural failures that we can find in these two categories differ. And I exemplified here the main failures that we can meet, and then we are going to look at this type of failures and how and whether we can detect them using our methods. And I mentioned the slope failures. The slope failures are more characteristic to the open pit mines. Here we can have either progressive movement, so we have displacement that is low in magnitude and is happening over time, a few millimeters, centimeters per month or per year, respectively. And these in time lead to a slope failure, so a landslide. Here we have an example from the Bingham Canyon mine in US that experienced a massive wall collapse in 2013. And what is interesting to mention in this case is that actually these progressive movements that led to this slope failure were detected in time using remote sensing, and the area was evacuated, and no casualties happened in this case. So it was quite a nice example of using remote sensing with positive outcome. We have then the roof faults that are more characteristics to the underground mines. These incidents appear as sudden sinks, or they can also be happen due to progressive movement in, for example, more in flooding conditions. So when the soil is wet, the season is rainy, then we are going to have this kind of failures because of progressive changes in the surface of the on the surface of the mine. We have mine floodings, and for mine floodings, we can meet in both cases, in open pit mines, but also in underground mines. We have sinkholes, and sinkholes are usually sudden. I mean, they seem sudden, but actually are often preceded by subtle ground deformation over months. So this makes them this can make them benefit from INSAR monitoring. And then we have tailing dam failures, which are a problem because usually the dams from the mining areas are keeping toxic materials, and we don't want those to be spread in the environment. And I give here this example from Brazil. This was quite recent, from 2019, and maybe you remember this incident when millions of cubic meters of sludge coming from mining was released in the area. And actually this led to more than 200 casualties. And what is sad is that this could have been prevented because post-monitoring, so actually historic analysis of the images that were taken by satellites before this event, showed that the movement that led to this dam collapse was actually seen by the satellites. So if this dam would have been monitored before the incident, then this could have been prevented. That this area could have been evacuated. Yeah, and here I put examples for each of these areas, with the tailing dam failure being the last. So now we know what types of movement we can detect with INSAR. Like what are the structural failure that we are interested in. But we have certain types of movement that can be detectable by INSAR. So when we are looking at the movement that we're interested in, we have to have in mind the characteristics of the movement and whether we are able to detect this movement using this technique. So INSAR is most sensitive to vertical and slightly horizontal displacements. We need a motion that is in the direction of the radar line of sight. So you have to think of your use case. For example, if you have a landslide happening on an open pit mine, then you might not be able to detect the whole the movements happening in the whole area. Okay, because in some of the slopes, the radar might not be able to see. If the radar is looking perpendicularly to your area, then you might miss some movements. Also, you have to have an expectation related to the type of movement, the magnitude of movement that you want to look at. Because if we are looking at cliffs or progressive slopes that are, for example, lower than 10 millimeters per year or a maximum of 5 centimeters per year, then INSAR is very effective in detecting these movements because they are slow progressive movements. But then if we have an accelerating failure or a sudden collapse, then the INSAR might just be correlated and not be that effective in detecting our future failures. So we have to have in mind the movement type when deciding whether we can monitor the area with INSAR or not. And knowing the characteristics of our site, then we will be in the situation where we would like to select the sensor, the most fit sensor, and we are going to take into consideration the resolution of the satellites. Sometimes if we need to monitor a larger area, then we can go with Sentinel-1, for example, which has lower spatial resolution, but it has higher revisit time and it can monitor a larger area at one time. But if we need to monitor like very small structures, so we are interested in bridges, in dams, and very like or just some small, very small sinkholes in the mining area, then we might want to go with commercial satellites, which are have a higher spatial resolution. In the case of Philippines and Manila, after our use cases, we saw that the area is quite covered in vegetation. So in this case, we would go with longer wavelength. Okay, so we would go with, for example, ALOS. If we would select a sensor that we would recommend for this kind of vegetated area. Okay, so this is the type of analysis that is done usually when we are selecting the type of sensor that we would like to use. So we have here the recommendations for the different bands and sensor that you could use depending on the use case. Of course, the use case related to the mining. When you're monitoring tailing dam, maybe the commercial satellites are the best because you are looking at very localized failures of the dams. Then you have the large area open pit mines, and here C-band can be enough because it covers a large extent of the area, and then you have good correlation because in an open pit mine you don't have vegetation. If you have vegetation like a vegetated surface, this can be characteristic to the underground mines. And in this case, maybe you will go with L-band. Yeah, and then you have the general high resolution deformation mapping in case this is required, or okay. Now, depending on the method, we already discussed the differences between the PS and SBUS methods. For the PS is best in urban areas, in arid, rocky areas with stable reflectors, but usually in the mining environment, we have natural areas, we have vegetation, and we tend to go more with the SBUS approach. So here we have an example of the same area being analyzed using the SBUS analysis and then the PS analysis. You can see that for for the same mining areas, you can see that the movement is similar. What it differs in this case was the magnitude of movement detected by the two methods. But in this case, the area that was compared was quite well covered in persistent scatterers. So in this case, the PS analysis was able to derive a density of points that was comparable to the one of the SBUS. Here we have an example of European open pit mine that was monitored using SBUS in SAR between May 22 and May 2023. And in this case, we have early displacement detected. We identified an acceleration in April 2023, and there was a failure prediction before failure that happened in the area. And this analysis was carried out in a continuous monitoring done by the DARES company. We do have some more examples that we also gave last time for different mining areas where we used SBUS to monitor, and but I also have my colleague here with me, Georgia, who is going to exemplify monitoring, so show you all the the application for the Siana gold mine in the Philippines. This is an open pit mine, and it also has an underground mining project. It had at least because this gold mine has been in operation for a number of years, but there was an incident that occurred in 2024 on May 11th, and since then the mining operation were put on hold. And this incident is being investigated at the moment. And actually, this is what we are going to look at right now, on whether the monitoring of these mining areas could have announced that failure is going to happen. And I have here the link to a website where we can actually see using optical imagery, what happened there in 2021. I will try to exit the presentation so I can. Okay. And if I go here, you can see the open pit mine. So we have here the main area of the operations, and here the tailing dam, yeah, holding the sludge. And then you can see, did you identify the area where it happened? Do you see the difference? So this is before and this is after. Okay, so this is the dam. Here it failed. And you can see that actually the sludge came over some residential area. Okay. So now Georgia is going to analyze the period preceding that failure to see if we could find some progressive movement that would have announced this failure. Thank you.